Okay, this one will be a very quick presentation about our demo that we have outside. I'm Giovanni Rovere, and I'm here with Florian Glaser, my colleague, and the title of our presentation is PULP Equipped SoC for Biopotential Signal Acquisition and Processing. So let me start with a brief motivation. You see on the top left graph US statistics that shows that the aging population trend, and this trend won't stop in the near future for sure. And this impacts in a negative way the healthcare system because it's getting even more expensive. This unfortunately because old people unfortunately require more healthcare than young people. So we can say that there is an increasing medical cost in industrialized countries due to aging population, and it's difficult to guarantee as well the fair access to high quality clinic healthcare services as well. So there are many solutions for this problem, and one of this solution could be the telehealth. So the telehealth is a user-centric healthcare. So right now, if you want to check your health status, you are forced to go to a hospital or to a clinic where then they can assess your health status because they have expensive equipment and skilled medical doctor that can do that. But this is part of the high cost of the hospital system right now, and our vision is that for certain kind of application we don't need to really go to the hospital, but we can sample our health status even continuously or within our home. Of course, to enable this user-centric view of the healthcare system, we need an application, we need a lot of things, but especially we need what I call the point of contact. So this is a hardware, this is a physical connection between your body and the digital world. So the wearable electronics can allow this, and you can record some specific signals like ECG, EMG, EEG from your body, and out of that extract some meaningful information about your health status. And the good thing is that you can also predict what will be your health status in the near future, so you don't have to feel bad and then go to the hospital. There are already some wearable electronics that does that, but the problem is most of the time they're not reliable and you cannot rely on them for healthcare systems. And also continuous acquisition is really difficult because they have a quite high power consumption. So just to give you let's say a numerical example, and in a real application, if you want to monitor your BPM, so the beat per minute of your heart rate, and also to extract some information like if your ECG looks like a healthy one or not, you can follow this very naive approach. So you have your A to D converter, so you acquire this data and then you transmit them over a wireless link, and then you do your computation in a powerful cloud. But since you stream a lot of raw data, this is a problem because the wireless link usually is the power bottleneck of the whole system. So our approach is actually to embed some computation in the point of contact, so really in your wearable, where you can extract information really locally and just send some metadata over the wireless link. So here you see a duty cycling of the power consumption at the system level, so you switch off whatever is not really needed. And yeah, the story started a couple of years ago. In ETA, we merged two different ASIC that belongs to two different groups. One is the analog front end. It's a low noise, flexible, and the PULP that you know very well. And we build a biopotential, what we call biopotential SoC. We tape it out, and this is the basic architecture. In yellow, you see the analog front end. It consists of 8 channels that usually are required for reliable healthcare assessment. These are differential, and these one are really the one that you can see outside. You can connect your arm to record your EMG. And a SAR ADC. A SAR ADC is chosen instead of a sigma delta, even though sigma delta has a little bit better power number. But a SAR ADC is much more flexible because it consists of really on a finite state machine, so you can control in a digital way. And then there is the PULP part that will be explained later. I will focus a little bit more on the analog part because it has two key, let's say, features. If you want to record real EMG data, you have this interface to your body. These are electrodes. And the signal of interest is very tiny. Here is the, you see is the red one in the big box. And superimposed to that, you have a large DC drift. So these cause a lot of problem to the analog part because it will saturate the analog part. You can get rid of that with decoupling capacitor, but usually they're very large and you cannot afford to integrate them on silicon. Or another approach is to use a digital to analog converter in order to compensate this, to estimate first and then to compensate this offset. This is one of the reasons we need a non-chip processor as well. And in this plot here, you can see how flexible is our SAR ADC. You cannot do that with the signal delta. You can, basically, you have a plane where you can trade it off the precision, that is the effective number of bits, the Nyquist bandwidth, so the speed, and also the power consumption. So according to your application, you can choose where to stay in this plane.
Okay. Now, let me give you quick more details about the use PULP architecture, so that you already know it quite well from the talk from Davide. The variant that we use only has 2 cores. For example, GAP is 8, normally we have 4, now we have 2, as a trade-off between the required processing power for the biomedical applications, typically required processing power, and not to inflate the area too much on the other hand. Then we choose a reasonable set of peripherals, also the two clock domains that are highlighted here. But then what is special is this standard peripheral connected here in the lower left that we call the analog front-end control. That is highlighted here in the light blue. And this in itself consists out of 2 different parts that interfaces the PULP to the analog world on the left-hand side through 2 buses. So we have the configuration bus on the upper left that maps the configuration registers of the various analog IPs, of which the SAR ADC is also one, to the memory space of PULP. So the registers are now directly accessible through standard operations through any one of the 2 cores. So if you want to configure an analog IP, you should just do a write. We have a specific addressing scheme. The data are put on the bus, and with an asynchronous one-hot IP select, they are then securely latched into the correct analog IP. And the other way around, the readout also works through an asynchronous signal, this time a data valid, going the other way around. And the current output datum is stored into a FIFO and could then also be read through a memory mapped register. But the idea here is more that this whole thing is event driven. So you can, for example, program a certain filling level of the FIFO or thresholds for the current output datum. And when then these conditions are met, the core can wake up and before it was sleeping and then react accordingly, so it doesn't have to run the whole time, which is the whole idea of the duty cycling that Giovanni already explained. Now that we told a lot about the system, we have development boards available, and one variant is sitting outside, where we are inviting you to join us during the coffee breaks. We can show you the live readout of both ECG and Emg signals, as Giovanni already said, with the electrodes connected to the arm. And for the ECG, we have some simple heart rate detection running on the PULP to show the processing part. Now let me give you the quick overview. Here on the left, we have all the characteristics summarized. On the top right, you have the chip micrograph with all the analog stuff sitting on the lower left. Yeah, quick conclusion. So we cover all kinds of different biopotential signals that we can flexibly process by application demand through our dual-core PULP subsystem here. Okay. Thank you for your attention. And
thanks, guys.